Hi everyone. So today, I believe we're on section 13. We're going to be talking about contradiction. So this is a second way of proving something. The other way that we've been using before is typically called a direct. So before I jump into showing you examples of this way of proving something, first I want to give you a loose idea of it. Okay? So let's say, let me actually label it as loose idea. So let's say you want to prove P is true. P is some statement. Okay, so maybe you're looking at P and you're like, wow, I have no idea how to show that that's true. But maybe the negation of P is a lot easier to prove false than P true. So if not P looks a lot easier to prove is false, if I want to show P is true, it might be easier to see that not P is false. So that's when I'm going to do proof by contradiction. Unless the test asks us to do proof by contradiction, then you definitely want to do proof by contradiction. Okay, so now here's what a loose sketch of a proof by contradiction is going to look like. First off, I'm going to actually call it proof by contradiction, okay? That's just a really nice way to let everybody know, listen, I know I'm assuming the wrong thing. I'm assuming the opposite of what we're trying to prove, but I'm doing this on purpose, okay? So now I've stated it, and then I'm going to assume the opposite of what I'm trying to show is true. I'm going to assume not P is true, okay? And I know what you're probably thinking is, Danica, you always tell us you can't try to assume what you're trying to prove. But in fact, I'm actually assuming the opposite. When I assume that the negation of P is true, I'm assuming that P is false. And so in the back of my mind, I'm going to try to go through this and show that this is not possible, okay? So I assume that the negation of P is true, meaning that P is false, and then I'm going to say a bunch of things that are true because of this, and then you'll see the punchline at the end. We'll look at some examples later, so we do a couple of lines or something, and then all of a sudden we get to stuff that's not possible. So maybe it's that a natural number is negative, or an integer is both even and odd, right? So that's not possible. And you may use this in your language. It's a contradiction. So if you contradict yourself when you're talking to someone, that means you say one thing and then you also say the opposite of it. And you state it as if both are true, right? And that doesn't make any sense. So then we get to say contradiction. And then I put an exclamation point. You don't have to put the exclamation point, but I love it. You can also write just C. So if you write just C, you're going to want to put the exclamation after it. Sometimes you could do C exclamation underline. That's my favorite. Okay, so now we've said, so there's something that's not true. You say a little blurb about why it's not true, why that's not possible. And then you say contradiction. Therefore, P is true, okay? And then we're done. Woohoo! Right? Because if we showed that it's not possible for the negation of P to be true, then P has to be true. Okay, so now we're going to do kind of an intense proof. This is mostly just to get you excited about the future of your mathematical career, and an example of a contradiction proof. So this is Euclid's proof of the infinitude of primes. So what we're going to do is we're going to show that the statement P, there are infinitely many primes, is true. Okay? So Euclid is a famous mathematician. You should totally look them up. It's a lot of fun. There's a lot of theories out there too. Even some that maybe it wasn't just one person. Maybe it was like a business. Very interesting. Okay, so let's start our proof. So you could write proof by contradiction like I did before, Or what you could do is you could somehow fit in by way of contradiction into your verbiage. So sometimes I'll do that if my proof is very long. So maybe I have like multiple tiny proofs inside of one big proof. So sometimes if I have a contradiction proof inside of it, I'll say by way of contradiction, assume blah, blah, blah. Okay, or you could do like I'm about to do here. I'm just going to put it in parentheses. This is a very much choose your own adventure class. Okay. So I'm going to assume not P. Meaning that there's finitely many primes. Say N. Okay, so there's finitely many. I'm just going to call it N. So see, if I said 3, that wouldn't give me a contradiction because that's just an example. Okay, so I need to say you choose any finite number. I have a proof that you can plug that number into, and I'll show you that that's not possible. Okay, so you cannot do proof by example here. Okay, this is the point of the class that I would ask for questions and things. So if this is hard to understand, that's understandable. This is a hard concept. Feel free to email me, reach out to your professors or your instructors. You can post on Piazza, email, all kinds of things. Okay? All right. So an advantage that we have for finite numbers, we can actually count them, right? So let's enumerate or number our primes. So next, I'm going to use the fact that any integer can be written as a product of primes. Then I'm going to consider just some number. So remember, you can always ask your reader to consider something. And so I'm picking this strategically. Okay, so I'm going to let capital M equal P1 times P2 times et cetera, times Pn. And then after that, add 1. So since the PIs are all integers, then M is an integer. So remember, this means for all I. But then I actually want to list out who the i's are. So then M can be written as a product of primes. And so that's because it's an integer, right? So that's what I said before. I said any integer can be written as a product of prime numbers. Fabulous. Therefore there exists some j, some number j between 1 and n, such that pj divides m, right? Because m has to be written as a product of primes. So since m is a product of primes, then we must be able to pick one of those and it must divide m. So now we're going to do a little bit of algebra. So we have this from before. Then let's rewrite it with 1 on the left-hand side. So 1 equals m minus p1 pn. So now we have it written like this, and we have, so pj divides this thing because pj's in there, so it's a multiple of it, and pj divides m from before. So there exists, so by definition of division, there exists a k and an l in the integers such that 1 equals pj k times k minus pj times l. Okay, so pj times l is this thing, and then pj times k is m. Okay. All right. So we can combine these two. Now we have pj times k minus l equals 1. Wait a second. K and l are integers. We can subtract 2 integers and get another integer. That means that pj divides 1 by definition of division. So you can also write this for a then statement. Then pj divides 1. Wait a second. That feels fishy, doesn't it? So what do we know about pj? Pj is a prime number. Contradiction. So it's not possible because a prime number can't divide 1. Only 1 or -1 divides 1, and neither of those are prime numbers. Okay? So, not possible. Therefore, there are infinitely many primes. Okay. So that might have been crazy and very fast, and I did intend it to be that way because I just wanted to get through it to show you an example. You don't need to memorize that. I just wanted to show you an example of something that you might see in the future. In the future of your mathematical career, not necessarily in this class. All right, so now let's look at a problem that is doable for this point of the class. Okay, let n be an integer, prove that if n squared is even, then n is even. So if you would like to write it in statement form, this is how you can do it. And then what we want to prove is that P implies Q. Okay? So if we want to prove this by contradiction, we want to look at the negation of that. Now, if you watched last video, you should know what this is. That's right. I'll assume you said the right thing. It's this. So we're going to assume that this is true and show that that's not possible. Okay? All right, let's get to it. Okay, so what are we assuming? We're assuming the if part is true and the then part is false. So we're assuming n squared even and n odd. Okay, so now I'm just going to start talking about definitions. Okay, for me, that's always the best way to go, and that's the advice that I give. You're not always going to write things that you're going to use later. Like not every single thing necessarily will be used later, but it is helpful. So this is the definition of being even and odd. So let's see. Like I said before, taking the square root of things gets a little iffy. So why don't we look at this and square it? Consider n squared 2k plus 1 squared. Oh, okay. Well, this looks familiar to a previous problem we've done. Okay, so we have that. So remember, we're trying to do this by contradiction. So we want to find out that something isn't right here. Well, if we're assuming that n squared is even, one way that we could go about this contradiction is to try to show that if n is odd, then n squared has to be odd. I hope that rings a bell, because that's where we've seen this before, is when we prove that n is odd if and only if n squared is odd. Okay? All right, so we're going to do something similar as that time. So we pull out a 2 just out of these first two terms, and we leave the plus 1. Okay? And now since k is an integer, 2k squared plus 2k is also an integer. Therefore, n squared is odd. But we assumed that n squared is even. Contradiction. An integer cannot be even and odd. I keep scaring my bunnies because I'm getting so excited. I love contradiction proofs, let me tell you. I try to turn every proof into a contradiction proof. Okay. Therefore, n squared even, then n is even. Woohoo! We proved it! Boom. Okay. So, it is actually true that n even if and only if n squared even. Similarly with the odd. Okay? Alright, this is our next example. So we want to prove that the square root of 2 is in the set the reals minus the rationals, which just means the irrationals. Okay? First things first, what do we want to assume? Well, we want to assume the opposite, right? The negation. So if square root of 2 is not in the reals minus the rationals, well, square root of 2 is still in the reals, So then that must mean it's in the rationals. That's what the negation would be, right? So assume it's in the rationals. Okay, so now here's when I start talking about definitions. So what does it mean to be in the rationals? Well, by definition, that means that there exists an x and a y in the integers, such as square root of 2 equals x divided by y. Okay, so that's great. I don't really know where to go from here. Ooh, but if we remember correctly, we're in the reals / rationals, so division is okay, and multiplication is okay. All right, so I can multiply both sides by y. And remember, y can't be 0 because we can't divide by 0. So it's okay to multiply both sides by y. So now I'm going to use that fancy symbol for then. Y times square root of 2 equals x. Fabulous. So now I'm going to kind of take a leap of faith. Okay, so it kind of seems to me like maybe what I'm going to do is I'm going to square both sides. And so why I'm thinking that is because the whole point of this is square root of 2 is hard to work with, okay? Like if you're an irrational number, it's pretty hard to work with you. So if I square both sides, then I have a 2. So then maybe I can say something about even or odd because 2 does a lot of stuff with that. So that's kind of where I'm thinking about going. But first I want to reduce the fraction x over y. Okay, meaning that like I don't want, let's say 2 over 4. Okay, I'd rather just have 1 over 2. Right, that's just easier to work with. I don't have to worry about as much things. Okay, so what that means is that would mean that x and y are relatively prime. So they have no common divisors except for 1. Okay, but first I'm going to introduce you to something called WLOG. So it means without loss of generality. So this is fancy math talk for I'm about to assume something, but it doesn't weaken my proof. Okay? Like I'm allowed to do this. All right? Is basically what I'm trying to say. And so without loss of generality, we can assume x and y are relatively prime, meaning they have no common factors. Okay? So instead of 2 over 4, now I've fixed it, I have 1 over 2. Okay? And every single fraction can be reduced like this. But if you're already handed 1 over 2, then boom, they're already relatively prime. Their only common divisor is 1. Okay? All right, so now I've got some nice things to work with. And if you did pause this video and you tried this on your own and you didn't do all these certain steps, please do not be discouraged. It's about trying. It's about jumping in even when the water is cold so that you can learn. Okay? So a lot of times we learn a lot more from failing than we do from copying or watching. Okay? You want to try on your own, learn, and then also try to teach others because that's a big component of this that could really help. Okay, so now I want to square both sides. We get y squared equals, 2 times y squared equals x squared. And if you had this problem, you're probably not going to come up with this right away. Maybe you have some trial and error. But, that's what you got to do, and then you'll start picking up on patterns of things, or you'll have like this tool set that I talked about before, and you have like common things that you can try out. Or you could think about like, okay, well, what could go wrong? Where could my contradiction come from? Well, I know a lot of things about even and odd and stuff like that, so maybe it has to do with that, and then maybe make some progress there. Okay? Since x and y are integers, then x squared and y squared are integers. In fact, we have that x squared is even, so x is even. Okay, and we just proved that above, so that's super exciting. All right, so now we have that x is even. So part of being even, it means that 2 divides you. So since 2 divides x, 2 cannot divide y, because remember, they don't have any common factors. Okay, so y must be odd. And why is that? because if you are even, 2 does divide you, okay? 2 does divide 0 and all the other evens, okay? So then if 2 doesn't divide you, well, you can't be even. So what do you have to be? You have to be odd. Okay? All right, so let's say we could approach this 2 ways. Let's start with talking about x. So since x is even, there exists, let's say, m in the integers such that x equals 2m. Then we have x squared equals 4m squared. But from before, we know that x squared equals 2y squared. Okay, so we're going to keep that on the board. So we are in the reals / rationals, so we can divide by something non-zero. Of course, you can never divide by 0, but we can divide by something non-zero. So we can divide by 2 to get 2m squared equals y squared. Wait a second. Since m squared is in the integers, then y squared is even. And what does that mean? That means that y is even. Contradiction. Y can't be even and odd. Boom! Roasted. Therefore, square root of 2 is in the reals minus the rationals. So, the irrationals. Okay, so this one is a bit simpler. So if the last one was a little intimidating, I believe in you. I think you could do this one. So try this next one on your own. Okay, so this one I would like you to try to prove on your own. I'll get us a little bit started. It might help if we do quantifiers. So say that these are our quantifiers. First, we want to think about what it is that we're trying to prove. And then let's think about what the negation of that is. Okay, so pause here again for that. Okay, so the first line is what we're trying to prove, so then we want the negation because we're doing this by way of contradiction. Okay? So now pause, try it on your own. I'm going to fly through this. All right, proof by contradiction. Assume x is in r minus q, r is in q, and x plus r is in q. So because these two things are in q, there exists, let's call them a, b, and integers, such that x plus r equals a divided by b. Then, so I'm trying to get to this thing. X equals r minus a divided by b. But we know that the rationals are closed, or if you subtract 2 rationals, you get a rational back. So we could just say that, or we could say there exists a k and an l in the integers such that r equals k over l. So x equals that thing. Therefore, x. So what I'm trying to say here is that the numerator and the denominator of x are in the integers. But I'm not going to say that k, b, a, l are in the integers again because that's already part of my proof. And x is not in the rationals as assumed. Contradiction. Not possible. Therefore, if x is in the irrationals and r is in the rationals, plus r is in the irrationals. Yay! Cool, cool, cool.